I've already built Tic Tac twice. In fact, I believe it's one of the top results you get when you search easy coding projects for beginners on Google. So why am I back here again? Third time's a charm? Well, actually, this semester I took the Fundamentals of Artificial Intelligence course where I was introduced to the absolute basics of artificial intelligence in games. And while I don't think I'll be building a deep neural network anytime soon, I thought it would be fun to apply what I learned this semester and build impossible tic-tac-toe with the Minimax algorithm. So what is Minimax? Imagine you're playing chess. To make the best moves, you need to not just think about your immediate advantage, but how your opponent will respond to your moves as well. Your goal is to maximize your advantage, while your opponent's goal is to minimize it. This back and forth process, thinking several moves ahead, is the essence of Minimax. You consider the worst case scenario, your opponent's best response, and try to ensure the best outcome for yourself. More formally, the Minimax algorithm is a decision-making algorithm which is more commonly used in turn-based games. It works by simulating all possible moves in a game and using these future states of the game to determine the best current move. This is done recursively, alternating between a maximizing player and a minimizing player. The maximizing player aims to maximize their score, while the minimizing player aims to minimize the advantage of the maximizing player. The algorithm assumes both players are playing optimally and recurses along the different paths in the decision tree of the game to determine the current move with the best future outcome. It does this using a formula that looks a bit like this, where I is the index of the player, minus I is the index of every other player except the current player, A is the action chosen by a player, and Pi is the value function of the player I. And now that I've lost half of your attention by introducing math into this situation, let's move on to efficiency. So in a small game like Tic-Tac-Toe, Minimax is pretty efficient because there's a limited number of moves that each player can make, which means that Tic-Tac-Toe will have a relatively small decision tree. However, in more complex games like chess, the number of possible moves grows exponentially. So this leads to a very large decision tree and a too many choices, too little time situation. To address this, the algorithm can limit how far ahead a player will look. Instead of searching the entire decision tree and determining the outcome of the entire game, we can just determine 5 to 10 to some number of moves ahead. This maximum search depth prevents the algorithm from taking too long to make a decision and allows you to finish a game of chess before you turn 63. We can still make the algorithm even more efficient by using an optimization technique called alpha-beta pruning. This optimization technique reduces the number of nodes evaluated in the search tree by eliminating branches that cannot affect the final decision. In doing so, we reduce the number of calculations made and in turn reduce the overall complexity of the algorithm. For the purposes of this video, we won't be exploring alpha-beta pruning since Tic-Tac-Toe can work without it and my brain might hurt with it. However, feel free to look it up if it's something that you're interested in since it is a pretty cool optimization technique. And now that we've gotten the math and algorithms, efficiency, and boring stuff out of the way, we can move on to the fun part and make the thing work.
So, as mentioned previously, I would have built Tic-Tac-Toe twice in the past. The first version of this was built using HTML, CSS, and JavaScript, and it was supposed to look a little bit like this. Unfortunately, though, due to circumstances definitely in my control, it looked more like this because I got bored and ended up never finishing the project. The second version of Tic-Tac-Toe was built using React.js, and I built this following the React.js tutorial, which teaches you a little bit more about state management in React using the game of Tic-Tac-Toe as a walkthrough tutorial. And as you can see, it's a standard Tic-Tac-Toe game, which looks a lot better than the first version that we just saw. And since I do plan to reuse one of my old versions of Tic-Tac-Toe to build on top and add the Minimax algorithm, I'm pretty sure by now you can guess which one I plan to use. With a little bit of movie magic, I've added some styling changes to the layout of the game, as well as some responsiveness for mobile so that we have a little bit cleaner of a style. And this is our starting base for the code of the game, which is pretty much everything in one file besides the implementation of the square component. So jumping straight into it, we'll go ahead and start by implementing our Minimax function, which we're also going to document to follow the rest of the standard of this code. And inside of the Minimax algorithm, we're actually going to pass in a copy of the squares that we have on the page so that we can see what we're currently working with and what the current state of the game is in order to make any additional changes. Since we're using recursion, the first thing we'll do is set out our base case, which in this scenario is when the game ends. So when we win, lose, or draw. So the next thing we'll do is set up our maximizing versus minimizing condition. So if the player is currently maximizing, we'll want to run one particular set of rules, and if they're not, then we want to run the opposite set of rules. So we'll do this using a Boolean variable, which will be passed into the function, and we'll check if the current player is maximizing. If his maximizing is true, then we'll run those conditions. Otherwise, we'll run the minimizing conditions. The first thing we'll do is initialize our max val to -infinity so that anything that we get higher than that will be our maximum value. Now we're going to want to check all of the available squares, which is going to be in the set of squares that are passed into the minimax function, and we want to see out of these possible squares, which move will give us the maximum gain, since we are playing as the maximizing player. So we'll call the minimax function recursively inside of this maximizing player set of rules and try to determine what is the maximum possible gain for this player. So we first start by checking to see if the current square that we're looking at is available. So we check to see if the value is null, and if it is, then that square is available. So knowing that that square is available, then we can go ahead and mark that square as if we played it. So for this game, we're actually going to denote the AI as the player O, while the user is going to be the player X. After marking that square, we'll calculate the value of the move that we just made by calling the minimax function recursively, and this time we'll pass in the set of squares that has the current square marked off, as well as the maximizing boolean set to false, since we just played the maximizing player and the next turn would be for the minimizing player. So now that we have calculated the value of the move we made, we want to undo it since this is just a simulation and it's not the actual move that the AI is making. And as you can see, there are several typos in this function that are going to come back to bite me in the butt a bit later, but we'll get to that when we get to it. So now that we've calculated the value of the move that we just made, we want to check to see if this is the maximum value that we can get, as that is the purpose of the minimax algorithm. So we get the maximum between the current max value and the move that we just made. And as you can see, my eval is highlighted red because I'm pretty sure that's a keyword, but I'll fix that in a second. And I will just go ahead and do the same thing for the minimizing player, but everything in this instance is going to be the opposite. So as I just mentioned that, you'll see another typo that I made very shortly, where I did not set the min val initially to infinity. I set it to -infinity, which meant that my min val was never going to be updated because I was getting the minimum between -infinity and values higher than. And to rectify the eval issue, I ended up changing all of the variables with the name eval to curval, which I think is a better representation. So I'm pretty glad that that happened and helped me to improve my naming convention. And now when I go ahead and play, you can see that I'm still playing as normal with no AI interjection since we have not called our minimax function. So we're going to go ahead and use this minimax algorithm now as a way to calculate the best possible move for an AI given the available squares. So calling this function best move, it will actually take in the set of squares that is also available to the user so that this can be passed onward to our minimax algorithm, which we are going to call inside of this function. So this part of the algorithm is actually going to work pretty similar to the maximizing part of Minimax, where we're going to initialize a best score and set it to negative infinity to be updated with the best score that we find as we explore the possible moves. So we'll do something pretty similar to the Minimax algorithm, where we iterate through all of the squares that have been passed into the function, and we check to see whether or not the current square that we're at is available or not. Because if it's not available, then we can't make that move, and it makes no sense trying to calculate the possible scenario. And I'm sure at this point, some of you are absolutely yelling at your screens that I just made the same typo that I made in the Minimax function. But I'll just learn the hard way and never make that mistake again. So yes, we go ahead and we set the temp squares at the current position to O to signify that we have made this move, and then we calculate the best score in a similar way that we did in the maximizing function in the Minimax function. So this part now goes ahead and unmarks the same value, and then we do the same thing where we find the best possible score given the best available moves. So as mentioned before, Minimax works recursively. So this function will be our launching point where we initially call Minimax to find the best current move with the given set of available spaces. And then using that, Minimax will work recursively, alternating between the players to find out which move is the absolute best based on the current position of the board. So we find the best score, set the value move to the index of that best score, and return that move. Now we actually need to call this function best move by allowing the AI to play. So I'll do some restructuring here where we set up to allow the user to make their normal turn, but we don't really need this if X is next function anymore, since there's only one user and that person will always be X. So we did some adjusting there, and then we go ahead and set up for the AI's turn. So we're going to make a copy of the current squares after the user has played and pass this set of squares into the best move algorithm so that we can find the best move that the AI should make and use that move as our next play. And this is the part where I start to realize the errors of my ways. And I say errors plural because there were several. So I decided to go ahead and try console.logging, doing some debugging and finding where I was referencing the entire array instead of referencing the index inside of the array. There was the point where I had set the minimum value, the original minimum value, to be negative infinity when it should have been infinity. So I discovered that at this point as well, where I console.log the score and I was seeing something that looked a little bit off. So I decided to go back and check, and upon further inspection, I realized, oopsie daisy, there we go. And just like that, we have a fully functioning game. And this was pretty cool. Like, this was the intent of the Minimax algorithm. I'm only ever losing or drawing. I'm never actually winning. The AI may win sometimes though, but I could not win. Impossible tic-tac-toe. But I wanted to go ahead and add a depth variable to the game, particularly in the Minimax algorithm, so that the AI makes the soonest best move instead of always going for a move that it knows is going to win at some point in the future. Adding a depth value would kind of incentivize it to win a little bit faster if possible and make it a little bit more aggressive. And that's exactly what I did. So we add some depth to the minimizing player so that it makes their score a little bit higher the further along they go, and subtract from the maximizing player to make the score a little bit smaller, which, as you know, would be the opposite of their aims. Then we just add the parameter to the function calls as well, increasing the depth as we go. And that is essentially the whole scenario of adding in this depth variable to make the AI a little bit more hasty. And that is our final game. As you can see, it's functioning as we expect. I am only ever losing or drawing. I can't beat the AI, unfortunately. I even tried going back in some of the moves just to show you that you can go back and try, but it's still always going to make the optimal move. And you're only ever going to lose or draw. As you can see, X never gets a highlighted row. And the final thing I did was to go ahead and update my documentation for tic-tac-toe so that we can have impossible tic-tac-toe. And as you can see, the site is live, so you guys can go ahead and try to beat it if you can. But I did host it using Render. This was hosted previously, so this is not a new thing. But yeah, go ahead and check it out.
And that is Impossible Tic-Tac-Toe. I want to thank you guys so much for watching, encourage you to try implementing this on your own, and even include some alpha beta pruning if you're brave enough. But until next time, this has been Technically T, wishing you a Merry Christmas and a Happy New Year. Bye!